Hello everyone, this is Firoz Nadav. In this video, we will see the development of stiffness matrix for the structure for the continuous beam given on the screen, and this question was asked in Mumbai University question paper in December 2022. You see that if the coordinates are given in the beam, then according to the coordinates we have to develop the stiffness matrix. In this question they have not given the coordinates. So first what we have to do, we have to find how many number of coordinates will be there in this particular structures, how many number of coordinates will be there in this particular structures, and also we have to number the coordinate, numbering the coordinates. After getting how many number of coordinates will be there in the structure, then after that we have to number the coordinate. So how to find the number of coordinates? We have to find dk, degree of kinematical indeterminacy, which is also known as uh, degrees of freedom. I will write here degrees of freedom. Okay, so first you need to find the degrees of freedom of this continuous beam. We can go to each and every joint. At joint A is having a hinge support, so it will not have a vertical deflection as well as it will not have a horizontal deflection, but there will be rotation at joint A, and rotation will also be there at joint B. Horizontal deflection will not be there at joint B. Since A is having horizontal reaction, there will not be any horizontal deflection of the B. Okay, so B will have the rotation and C will also have the rotation. Okay, so we have three number of coordinates. So first is we have to define the number of coordinates. If the coordinates are not given, then we have to number the coordinates. So I will number like this: coordinate number 1, coordinate number 2, and coordinate number 3. After assigning the coordinates, we have to apply unit rotation and at all the coordinates, and then we need to find the forces in all the coordinates. You see, I'm using the term applying rotation or applying deflection. Applying rotation is not correct. Only for the understanding purpose I'm using the word applying, because rotation and the displacement, it cannot be applied. It is the byproduct of the forces. Okay, so what we have to do, we have to apply the rotation at all the coordinates, and then we need to find the forces because of that rotation. So when you are applying rotation at a particular joint, you have to assume that the other joints are fixed. For example, you are applying unit rotation at joint A, then you have to assume that joint B and joint C are fixed. And when you are applying rotation at joint B, you have to assume that joint A and joint C are fixed. Okay, so first we will apply unit rotation at coordinate 1. Okay, write down applying applying unit rotation at coordinate 1 at coordinate 1. Okay, and then we need to find the forces developed at 1, 2 and 3 because of the application of unit rotation at coordinate 1. We will see how to find that. Okay, so again I will draw the beam, continuous beam. A is having hinge support and the other joints are having roller support. You are applying unit rotation at A at coordinate 1. You see, the all the rotations, all the coordinates are having clockwise sign, so you have to apply clockwise rotation. So here the rotation is clockwise. Since the rotation is clockwise, this beam will sag. The displacement will be downward for this beam, for AB. Okay, so here you have unit rotation theta A is equal to 1. Okay, and since the other uh, ends are fixed, we are assuming that the other ends are fixed, no rotation is developed at joint B and joint C. Okay, So you see theta A, you're getting some rotation since you are applying some force here at A. At A you are applying some force, and because of that force you are getting unit rotation at A, and that force is 4 EI by L. Okay, so you have to apply 4 EI by L to get unit rotation at A. And since the far end is fixed, some moment will also produce at the far end, that is 2 EI by L. Already you have seen the concept in moment distribution method. So whenever you are applying some moment at a particular joint, if the far end is hinged, if the far end is hinged, half of the moment is transferred to the far end, or you can say half of the moment is developed at the far end, and that concept is known as carryover factor. Okay, so you can write K11 force required at 1 to produce unit rotation at 1. So what is the force required at 1 to produce unit rotation at 1? Force required at 1 is 4 EI by L. 4 EI by L. By the way, they have given different value of moment of inertia for AB and for BC, and also they have given different length. You have to consider that. Okay, so 4E into 2I for AB. So these moments that are developed, it is with respect to AB only. Okay, so you have to take the moment of inertia of AB, and also you have to take the length of AB. So length of AB is 6 meter. So K11 equal to 8 EI by 6. Now you see what is the moment developed at coordinate 2 because of unit rotation at coordinate 1. K21 force required at 2 to produce unit rotation at coordinate 1. So what is the force developed at coordinate 2? The force developed at coordinate 2 is 2 EI by L. So this is the force at coordinate 2 to produce unit rotation at coordinate 1. Okay, so 2 EI by L, you have to substitute the value of I and L. 2E into 2I divided by L. So what is L here? L is 6 meter. So 4 EI by 6. And you see no moment is developed at coordinate 3. So K31 force required at 3 to produce unit rotation at 1. So since no moment is developed at coordinate 3, so K31 will be equal to 0. Now we have to apply unit rotation at coordinate 2, that is joint B. Okay, so to get the unit rotation at coordinate B, you have to apply some moment at joint B, and that moment should be clockwise because you have assumed that coordinate 2 is clockwise. So when you are applying clockwise moment to joint B, BC will go down and BA will go up. Okay, so you see like this you will apply. What will happen to BC? BC will go down, and accordingly you have to draw the deflected shape of BC, and BA will go up, and accordingly you have to draw the deflected shape of BA. Okay, so it will be like this. It will be like this. I will draw. It will be like this. BC will go down and BA will go up. Okay, so this is your theta B for BC span, theta B for BC span, theta B is connected to 2 span, so you will have 2 rotation, theta B for BA span, theta B equal to 1, theta B equal to 1. Okay, so since the other ends are fixed, no moments are developed at the other end. We have to assume that whenever you are applying unit rotation at any joint, the other joints will be assumed as fixed. Okay, so here the force will be 4 EI by L. I for BC span is 1.5 I. You have to consider that 4E into 1.5 I divided by span of the BC is 4 meter. Here theta B, here also you will get 4 EI by L, 4 EI by L, but this is with respect to span BA. Okay, so 4 EI by L, moment of inertia for span BA is 2I. 4e into 2I divided by L. L is 6 meter. Okay, and you see at the far end, half of this moment will be developed at the far end, that is from the carrier factor 2e into 2I divided by 6, and here also half of the moment will be developed at the far end, and that from the concept of carrier factor 2e into 1.5I divided by 4. So now we can write the stiffness matrix K12, force required at 1 to produce unit rotation at coordinate 2. So what is the force developed at coordinate 1? What is coordinate 1? Coordinate 1 is joint A. Some forces are developed at joint A because of unit rotation at joint B, that is 2 directly I will write 4EI by 6. Okay, K22 force required at joint force required at coordinate 2 to produce unit rotation at coordinate 2. By the way, we have two forces at coordinate 2. Joint B is connected to 2 beam. Okay, so we will get two forces. I will write here 4e 2I divided by 6 plus this is with respect to BA, this is with respect to BA, and one more force we have, that is with respect to BC. Okay, so 4E into 1.5I divided by 4, you can solve this and you will get the answer 2.83 EI. K22 equal to 2.83 EI. Okay, now we will write K31 K31, sorry, not K31, K32, K32, because you are applying unit rotation at 2. So what is K32? Force required at 3 to produce unit rotation at 2. So what is the force developed at 3? That is 3EI by 4. Now what we will do, we will apply unit rotation at coordinate 3, and then we will find the forces at 1, 2 and 3. Okay, so again I will draw a continuous beam. Here it is hinge support, and here it is roller support, here it is roller support. So at coordinate 3 I have to apply the unit rotation. For that I have to apply the moment, and because of this moment, what will happen to span CB? CB will go up. Okay, it will hog, and accordingly you have to draw the deflected shape of CB, and you have some rotation here, theta C equal to 1, and the force will be 4E, and I of CB is 1.5 I divided by L of CB is 4, and half of the moment is developed at the far end, because you are assuming that the far end is fixed, 2E into 1.5 I divided by 4. No moment is developed at coordinate 1. So accordingly you can write K13 force required at 1 to produce unit rotation at 3. So no force is developed at 1. K13 is equal to 0. K23 force required at 2 to produce unit rotation at 3. Some moment is developed at coordinate 2. Then you have to take that. K31 K23 equal to 3I by 4, and K33 force required at 3 to produce unit rotation at 3, that is 4 into 1.5, okay, 6 EI divided by 4. Okay, so after doing this, we can we can write the stiffness matrix K equal to K11 K. We have three coordinates. The size of the stiffness matrix will be 3 by 3. Okay, K21, K31, K12, K22, K32, K13, K23, and K33. Okay, so already we have calculated the forces in all the coordinates. We can write it down. K11 is 8 EI by 6. K21 is 4 EI by 6. K31 is 0. K12 is 4 EI by 6. K22 is 2.83 EI. K32 is 3 EI by 4. K13 is 0. K23 is 3 EI by 4. K33 is 6 EI by 4. Okay, so this is the stiffness matrix that we have developed. Thank you for watching my video. Thank you very much.